Alright, what we're looking at now is reflection. Hopefully you've looked at that first video where we looked at waves in general. So let's look at reflection. We get reflection with water waves. We certainly get it with that. We get it with sound. We get it with light waves. Let's just go with our usual light reflection situation where we've got a mirror, maybe in a bathroom, and you put an object, and I'll just draw a line so I can see. You put an object, maybe looks like a little arrow, in front of the mirror, and you can then see that arrow behind the mirror. But you know that if this was a wall, and maybe there's another room behind there, if you go behind there, you can't see the image. And yet, we often do this experiment where in junior science where we make the arrow a candle, and we try and find on the other side, and we don't use a mirror, we use a piece of glass, so we can see the reflection, and yet we can see through it. And we put another candle on the back till we match them into the same position. And we find that this distance here is exactly the same distance. And we find the object size and image size, so that's object size and image size, are exactly the same. Now you might be going, oh, so what? God, that's obvious. What's not going to be obvious is that with the curved mirrors and lenses, this doesn't happen. We get bigger images, smaller images. So what happens with the flat mirror is quite special. So the object size and image size are the same. The object distance and image distance are the same. All right, so that's quite special. Then you've got another thing that happens is left and right get turned around, right? So that's called lateral inversion. And that's because whatever gets, say, if you, we're seeing a one-dimensional object here, but if you had obviously a two-dimensional object, my thumb is going to be on this side of the mirror, and my finger is going to be on this side of the mirror, right? So, and yet, I'm going to be seeing the surface on this side, so this thumb might be on this side, but it's going to look like it's on the other hand on that side of the mirror. So it's quite interesting that it reverses things like that. Lateral inversion is an interesting thing. Okay, but what's actually happening? The key to all this, image, and when you hear me talk about image, it's just not an obvious thing. Objects have light rays going off at all angles from one, and try and always talk about one point on the object, because every point has billions of light rays. So we'll just talk about one point. Billions of light rays. So over in the mirror here, every point on the mirror has got a light ray from every point on the object. So it's a total mess of light rays. But the mirror does a very interesting thing, and a very special thing, is that if the angle that the light ray hits the mirror is a certain amount, then the reflected light ray will be the same amount. And that's called angle of reflection is equal to the angle of incidence. And it is very special. That's what enables an image to be produced. That's why you can see your beautiful face in the mirror. Otherwise, you would never see it. You might be able to see light rays, but you'd never see an image. There's another special thing that enables us, another special device called a lens, and you've got one in your eye that enables us to see an image. Images are very special. Otherwise, nothing would look like anything. So I kept these angles the same, theta and theta. And then I said, well, if someone was over here, this light ray would look like it came from over here, which is why I drew it back like that. I said, hey, it would look like it came from here. It's not really there, but it looks like it comes from there. And that's why we call it a virtual ray. And so when we're trying to find out where your eye perceives an object image to be, we always draw two light rays from the same point on the object. And we keep our whole angle of incidence, angle of reflection thing going. And what we find is that they will intersect at a point behind the mirror, the two virtual rays. And this is where the image for that point is. So that point is there. I've located it. I could do the same thing for a point here, and I'd find that it's here. And that way I'd know that my image was right way up. So this is reflection. It's pretty cool, and it's not just light rays. If we have a wall and we have waves coming in, sea waves, then they will do a similar thing. In fact, because my wall's like that, they're not going to be very interesting. What if I put a wall like that? Then what they're going to do, these waves are all going in this direction, right? So again, we can work out our angle, and they're all going to bounce off the wall like that. So you get the same thing with water waves and sound waves. When I drew these, I call these are my crests, if you like, and this whole thing would be the crest of the wave coming towards the beach, if you like, and it is called a wave front. Often we just draw the direction the waves go in, which is these arrows, but always remember we've got wave fronts, and if I characterize those as being on the crests, then this is your wave length. Now there's another thing I drew in here, this big thing here, which is perpendicular to the surface where the wave strikes, and that is called a normal. On my first diagram, I put one in here. That wave came in and went like that. These waves, these light waves, also have a wavelength, but remember it's so small, 1/2000th of a millimeter, we can't see it. So this is reflection.